So we're looking at gas mixtures. Yeah. So whenever we collect a gas with water, we have to assume that that gas is going to be saturated with water vapor. All right. So last time we were looking at this wet oxygen, correct? So what we have is we have pure oxygen being bubbled in here. And then as it bubbles through water, it picks up water vapor and becomes saturated. And so in here we have wet oxygen. What we want to know is how much dry oxygen, how much pure oxygen is in there. Because wet oxygen, what that is it's equal to pure dry oxygen and water vapor. H2O gas. But we don't necessarily care how much water vapor is there, but we need to know. We need to know that because otherwise we aren't going to be able to figure out how much dry oxygen there is. The amount of water vapor that's in there is going to depend on what? How big the container is? Yeah, the bigger the container, the harder it is to saturate it with water vapor. But what we're going to assume that there's plenty of water to saturate it. This would be like the indoor swimming pool. Do they still have the indoor swimming pool here? Have you been inside there?
I've seen it.
It's kind of humid in there. Have you noticed that? Like indoor swimming pools are pretty humid. Yeah, because there's plenty of water. There's plenty of water can completely saturate it. But what if, like, outdoor swimming pool, is it really that humid?
Not really.
No. All that water in the outdoor swimming pool could evaporate and still not saturate the air with water vapor. It would take some time for it to evaporate. But what they do is they just keep refilling it. You know, they have an automatic valve. As the water evaporates, they refill it with some water. And so we want to know the amount of oxygen. How much oxygen? The amount of oxygen is moles of oxygen. You know, if we do stoichiometry, well, we need to know how many moles of oxygen we have. So this is going to be the moles of dry oxygen. The moles of dry oxygen will equal the what is it going to equal? We'll solve the ideal gas law. The moles of dry oxygen equals the pressure of dry oxygen times the volume of dry oxygen divided by R, the gas constant, times the temperature of dry oxygen. Well, let's do the easiest one first. The temperature of the dry oxygen. So will the dry oxygen in here and the water vapor have the same temperature? That is the water vapor colder or hotter than the oxygen, or the oxygen colder or hotter? What do you think? Well, both gases are in the same container. It's in a mixture. So if we put our thermometer in here, we're going to measure the pressure. I mean, not the pressure, the temperature of both. And so it turns out that the temperature of dry oxygen is the same as the temperature of wet oxygen, which is the same as the temperature of the water in there, etc. It's all in thermal equilibrium. R is just our gas constant. What is the pressure of the dry oxygen? Here's where we run into some potential difficulties. If I measure the pressure out here, this is the pressure of the atmosphere. And is the pressure of the atmosphere or the weight of the atmosphere the same as the weight of the wet oxygen in here? This will be the pressure of the wet oxygen. Are they the same? Well, it depends. It depends on the level. If the internal level here is higher, then the atmosphere weighs more. It's going to push this up. If the wet oxygen here has higher pressure, it's going to push this down and this up. Right now, they're level. So if they're level, it tells us that the pressure inside the container is equal to the pressure outside the container. Does that make sense? And so I know that P atmosphere is equal to the pressure of the wet oxygen here. The pressure of the wet oxygen is going to equal the pressure of the dry oxygen plus the pressure of the water vapor, H2O gas. Now, fortunately, if we're at 100% humidity, we can look this up. If at 100% humidity, then can find in table. This people have measured it. There are lots of these tables. Here. So the vapor pressure of water, it depends on the temperature, and we have to make sure we saturate it. So let's say today's temperature were 25.0 degrees C, then the vapor pressure of water is 23.756 millimeters of torr. And that doesn't matter how big the container is. The bigger the container, we have to have more water in there, but it's going to have the same vapor pressure. So a small container, big container will both have the same vapor pressure. And then once we get that, then we can solve for the pressure of the dry O2. The pressure of the dry O2 is just equal to the atmospheric pressure minus the pressure of the water vapor, H2O gas. And so this would be Dalton's law. The total pressure is equal to the sum of the partial pressures here. Okay, now we need the volume of the dry O2. What is the volume of the dry O2? Well, the volume of the dry O2 is going to be the same as the volume of the wet O2 because the dry O2 is going to hit the walls of the container. And the water vapor is going to hit the walls of the container. And both are free to move around the container. So the volume of dry O2 is equal to the volume of the wet O2, which is equal to the volume of the water vapor. All the gases occupy the same container here. So this is Dalton's. What's another way we can look at this gas mixture? Another way we could look at it is by mole fractions. Dalton's a pressure fraction. So a certain fraction or a certain percentage of the pressure is going to be generated by the black particles hitting the oxygen, I call it. And a certain amount of pressure is going to be generated by the blue. That would be the fraction of the total pressure. Dalton's, the sum of the partial pressures is equal to the total pressure. And so if I sum up all of the particles colliding, the black and the blue in this drawing, then that's going to give me the total pressure. What's the other way I could look at this? I could look at it as a Dalton's mixture, or I could look at it as what's the other? Avogadro's. And so if I look at this mixture using Avogadro's, what would that look like? So let's take a look at this. So I want to figure out the moles of dry O2. The moles of dry O2 is going to equal the pressure of dry O2 times the volume of dry O2 divided by R, temperature of dry O2. So using Avogadro's, the temperature of dry O2 is going to be the same as the temperature of the wet O2. There's no difference there. However, when we do Avogadro's, Avogadro's looks at volume fractions. And so if this is the entire volume here, then in terms of volume fraction, I should have showed the drawing for Dalton's up here. What we're going to do is we're going to divide the particles up. And so the oxygen gas will occupy a certain volume here. And the water vapor will occupy a volume here. And we're going to maintain the number of particles so that the pressure doesn't change. And so this will be the volume of the dry O2 here. This will be the volume of the water vapor. And so what we're going to get is the volume of wet O2, that is the total volume, is equal to the volume of dry O2 plus the volume of the H2O vapor. And these volumes are going to be adjusted so that the pressure doesn't change. Because in Avogadro's, the pressure of the wet O2 is equal to the pressure of the dry O2. So the pressure of the wet O2 is generated by the collisions of both the oxygen and the water vapor. But if we separate it so that we only have dry O2 here, no water vapor, then we need a smaller container. If we have the same size container, the pressure is going to drop like Dalton's. Here, a smaller container, we can maintain the same pressure. And the volume for the water vapor has to be much smaller as well because we have less water vapor. We want to maintain the same pressure here, so this will be the pressure of the H2O gas. The problem is we can't look this up in a table. And therefore, whenever we put gases over water, we look at it from the perspective of Dalton's. We can't look this up in a table, but can calculate it. So let's look at an example here of Dalton's and Avogadro's. Oxygen is generated for laboratory experiment by bubbling the gas through water, as illustrated in figures 15.3 and 15.4. The total pressure of the oxygen saturated with water vapor is 755 torr. P total is the pressure of the wet oxygen, and that's 755 torr. The pressure of the wet oxygen is equal to the pressure of the dry oxygen plus the pressure of the water vapor, gas. The temperature of the gas mixture is 22 degrees C. So all the gases inside the container are 22 degrees C. And the water vapor pressure at that temperature is 19.8 torr. Where did they get the vapor pressure of water? They looked it up in a table. And so the temperature is 22 degrees C. And so we go to this table here, and we go to 22.0 degrees C. And we see we have a vapor pressure of 19.827 torr. Go back over here. And they rounded it different. I would have rounded it to 19.9. This was 19.872. But it could be a different table we use, slightly different. But anyway, we'll just use 19.8 torr. At 22.0 degrees C. All right, from this, we're going to get the pressure of the oxygen. The pressure of the dry oxygen is equal to 755 minus 22.0 degrees C. And this is going to give us 733 degrees C. Oops, not degrees C, torr. Sorry, 19.8. I'm reading the wrong one. 19.8 torr, which is about 20, so 735 point, or 736, 35.2. Okay, so we have a total pressure of 755 torr. Out of that 755 torr, 735 torr due to the oxygens hitting the wall. So this is going to generate 735 torr, the pressure of the dry oxygen. In addition to the dry oxygen hitting the wall, we have water vapor hitting the wall. And the pressure of the water vapor hitting the wall, the H2O gas, is 19.8 torr, or about 20 torr. All right, so if I want the number of moles of oxygen is going to equal the pressure of the oxygen, which is going to be 735 torr, times the volume of the oxygen. Actually, we don't know what the volume is here. Divided by RT. Let's make up a volume here in a minute. Let's say we have a 1 liter volume. So that means V is 1 liter here. So the pressure of the dry oxygen, there are different ways of visualizing this. The pressure of dry oxygen is equal to the pressure fraction of oxygen. The pressure fraction of oxygen is 735 torr over 755 torr total. Times the total pressure of 755 torr, which is going to give us the pressure fraction of oxygen is 735 torr over 1. The volume of the dry oxygen is equal to the volume of the wet oxygen, which is equal to the total volume, in this case 1 liter. All right, so this is Dalton's. Let's go to Avogadro's. Okay, when I go to Avogadro's, I'm going to do one thing for this. I'll do that over here. The pressure fraction which is PA over P total, in this case A being the oxygen, is going to equal the volume fraction, which is VA over V total, which is going to equal the mole fraction, which is NA over N total. The pressure fraction is valid at constant volume. So I kind of ran out of room here, but we're going to split this up. In terms of constant volume, we're going to have 1 liter of oxygen. And so I'm going to take out just the oxygen from my mixture and put it into this 1 liter container. And the pressure is going to go down. Plus 1 liter of water vapor. So this will be 1 liter of H2O gas. And the pressure is going to go down there. So if I take 1 liter of oxygen plus 1 liter of water vapor, that's going to give me 1 liter of mixture. Here. But the pressure, if I take the pressure of the oxygen plus the pressure of the water vapor, this will give me the pressure of the mixture, the total pressure. In terms of Avogadro's, I'm going to do it like this. I'm going to maintain constant pressure. And so if this were 755 torr, then how much oxygen will I have? Well, I'm going to have 755 torr worth of oxygen. If I have 755 torr worth of oxygen, it's got to be in a smaller container. What size container is this? Well, if I take the pressure fraction, the pressure fraction is going to be 735 over 755 times the total volume, which is 1 liter. What does that come out to? So 735 divided by 755 times 1. 0.9735 liters. Carry extra digits. Okay, then I'm going to separate out the oxygen. I'm going to do this at constant pressure, so I'm going to need a smaller box for the oxygen. And I'm going to get a 755 torr worth of oxygen. And I'm going to get 755 torr of pressure worth of water vapor. What is that volume? Well, I can use the pressure fraction to figure it out. The pressure fraction is going to be 19.8 torr of water vapor over 755 torr total. Times the volume, 1 liter. $19.8 divided by 755 times 1. 0.0262 liters. This should add up to 1 liter. And so what I end up with is the volume of oxygen plus the volume of the water vapor, this is the dry oxygen, is equal to the volume of the wet oxygen. And that the pressure of the wet oxygen, 755 torr of wet O2, is equal to the pressure of dry O2, which is equal to the pressure of the water vapor. Does that make sense? Maybe confusing. It may take some time to get it. What's not confusing are these particular problems. These problems are pretty straightforward. So let's go back here and take a look. Oxygen is generated for a laboratory experiment by bubbling the gas through water, as illustrated. The total pressure of the oxygen saturated with water vapor is 755 torr. The temperature of the gas mixture is 22 degrees C, and the water vapor pressure at that temperature is 19.8 torr. What is the partial pressure of oxygen? And so all they're doing is the total pressure is equal to the sum of the partial pressures. There we have the pressure of the water vapor plus the pressure of the oxygen. And so the total pressure is 755. It's going to be the combined pressure of these two. And if we're solving for the pressure of the oxygen is equal to P total minus the pressure of the water. And so the 755 torr minus about 20 torr, which is going to give us 735 torr. So that's what we got over here. 735 torr of water vapor. Or not water, oxygen. This is about 20 torr of water vapor. So if we combine these, that's going to give us our 755 torr total. Calculate the partial pressure of oxygen in atmospheres in a sample collected over water, given that the total pressure of the mixture is 0.98 atmospheres. And the partial pressure of water vapor is 16.5 millimeters mercury. So what we did is get these in the same unit. And so this is the pressure of the wet oxygen. The pressure of the wet oxygen is equal to, the pressure of the wet oxygen is equal to this. The pressure of dry oxygen is equal to the pressure of the wet oxygen minus the water. So that minus that, but they have to be in the same unit. Okay, let's see, applying Dalton's law here. Let's take a look at the homework. Okay, let's take a look at these problems here. Why don't you take a look at these and then see. Figure out the answer. Forgot to record that. But this is some repetition of, I recorded in the morning too, so you can see it. I'm a little further ahead in the morning, so. Look at last week's lecture. A mixture of argon and carbon dioxide gases is maintained at 8.05 liter flask. So this is V total at a temperature of 43 degrees C. If the partial pressure of argon is 0.326 atmosphere and the partial pressure of carbon dioxide is 0.234 atmosphere, what is the total pressure in the flask?
So you're using Dalton's then? Because it's constant volume?
Yeah, the volume's constant, the pressures are additive. And so we just add these two pressures. So if we have 8.05 liter mixture, then it's 8.05 liters of argon and 8.05 liters of carbon dioxide. And so if we combine those, then we just add these two pressures. So the total pressure is here. Atmospheric pressure is the total pressure of the gaseous mixture called air. Atmospheric pressure is 749 torr on a day. The partial pressures of nitrogen, oxygen, and argon are 584, 144, and 19 torr respectively. What is the partial pressure of all other gases in the air on that day? And so most of Dalton's problems, Dalton's law problems are pretty straightforward. And so most of the problems are like this. P total for Dalton's is equal to the sum of the partial pressures. So in this case, what are the partial pressures? So P total is going to equal the partial pressure of nitrogen, oxygen, and argon. The pressure of nitrogen, pressure of oxygen, plus the pressure of argon, plus the pressure of the other gases. They give us P total, which is 749 torr. So 749 torr is the total pressure. That's equal to the pressure of the nitrogen, which is 584 torr, plus the pressure of the oxygen, which is 144 torr, plus the pressure of the argon, which is 19 torr, plus the pressure of the other gases. And so we just solve for the pressure of the other gases just by taking the total pressure and subtracting out all the other pressures from that. A sample of wet hydrogen gas was collected over water. The sample was adjusted so that it was at room temperature and pressure, 19 degrees C and 733 millimeters mercury. The water vapor pressure at 19 degrees C is 16.5 millimeters mercury. What is the partial pressure of dry hydrogen? So this is the pressure of the wet hydrogen. The pressure of the wet hydrogen is equal to the pressure of the dry hydrogen plus the pressure of the water vapor, which is here. So the pressure of the dry hydrogen is equal to the total minus the water vapor. Here. And so 733 minus 16.5 should do it. Sodium metal reacts with water to produce hydrogen gas according to the following equation. In an experiment, the hydrogen gas is collected over water in a vessel where the total pressure is 745 torr. So this is the pressure of wet hydrogen. And then they give us the pressure of the water vapor, 7.15. And so the pressure of the dry hydrogen plus the pressure of wet water vapor is equal to the pressure of the wet hydrogen here. Okay. All right, so number 6 is kind of a mix of Daltons and Avogadros. So can you figure out number 6? Try that. All right, so we have a container, a mixture of gases. And this container is going to be at a total pressure, P total 745 torr. That's going to be wet hydrogen. Wet hydrogen means we're going to have hydrogen gas and water vapor. And then we're going to assume that this is saturated with humidity, water vapor. It says if the wet hydrogen gas formed occupies a volume of 8.04 liters. And so V total is 8.04 liters. Okay, so I want to focus on the hydrogen, just the hydrogen. How much hydrogen do I have? Well, we need some more.
You need the temperature?
I need the temperature. What is the temperature? 2 degrees C. And then I go to the table. The table is the vapor pressure water table. And then I go up to 20 degrees C. Do you see the vapor pressure of water? At 20 degrees C, what is the vapor pressure of water? 17.535. And the units for this are torr. Torr. $17.535 torr. So if that's the pressure generated from the water molecules colliding with the wall, what's the pressure of the hydrogen? The pressure of the hydrogen is equal to, now this is not the wet hydrogen, this is the pressure of the wet hydrogen. This is going to be the pressure of dry hydrogen. And so what is the pressure of the dry hydrogen equal to? Well, it's going to be the pressure of the wet hydrogen, or the total pressure, minus the pressure of the water vapor. And so that's going to equal the pressure of the wet hydrogen is the total pressure, 745 torr, minus the pressure of the water vapor, 17.535 torr. I'll just do minus 18 torr. I'm going to round it anyway. And so what does it come out to? $723.22. $722 torr. Is that right?
We got 727.5.
727.5.
And I rounded it to 728.
728.
Yeah.
All right. 728 torr. So how much hydrogen do I have? Well, I know I have 8.04 liters of wet hydrogen. How many liters of dry hydrogen do I have? If I have 8.04 liters of wet hydrogen, how many liters of dry hydrogen do I have?
8.04.
8.04 liters. What is the pressure of my dry hydrogen? Yeah, 728 torr. The temperature of the dry hydrogen is going to be the same as the temperature of the wet hydrogen, 20.0 degrees C. So the number of moles is equal to the pressure of the dry hydrogen, 728 torr. Convert that into atmospheres. 1 atmosphere is equivalent to 760 torr times 8.04 liters divided by R, 0.08206 liters atmosphere per mole Kelvin times T, 293 Kelvin. So the torr cancel, atmospheres cancel, liters cancel, Kelvin cancels. And that should give me 1 over moles, which is going to come out to how many moles? So 728 divided by 760 times 8.04 divided by 0.08206 divided by 293. 0.3203. So I expect to have 0.3203 moles of pure hydrogen. We call it the dry hydrogen. How much water did I end up with? How many liters of water vapor? So I have that much hydrogen. How much water vapor do I have? I'm going to have 8.04 liters of H2O gas. What's my pressure of H2O gas? Pressure of the H2O gas was 17.5 torr, or I just rounded it to 18 torr. And so I have my volume, I have my pressure, and I need my temperature. Just 20.0 degrees C. And likewise, I can calculate the number of moles of H2O gas. So, I wanted to, but they're not asking for it. Is this Dalton's or Avogadro?
Dalton's?
Dalton's. What percentage or what fraction of the total pressure is due to hydrogen? So we'll do this over here. The pressure fraction for hydrogen is this. We had 728 torr of hydrogen over 745 torr total. And that's going to equal this pressure percentage. The pressure percentage is this times 100. And so let me calculate the pressure fraction here. It's 728 divided by 740 times 100. It's going to tell me it's 97.7 hydrogen. That means it's got to be 2.29% oxygen because they got to add up to 100%. So this is going to be 2.29% oxygen, or not oxygen, water vapor. So. The other way of looking at this mixture is via Avogadro's. So what would be different if I describe this mixture in terms of Avogadro's? In terms of Avogadro's, the volume, first I'm going to have the volume of the dry hydrogen. I have to use some data from earlier, and that is the pressure fraction is equal to the volume fraction, which is equal to the mole fraction, or the pressure percentage is equal to the mole percentage, which is equal to the volume percentage. And so the volume of the dry hydrogen is equal to the mole fraction so the mole fraction is going to be 728 over 745, or 97.71 over 100, or 0.9771 divided by 1. And so we have the fraction here out of the total volume, 8.04 liters, times 8.04. Let me try that one more time. 728 times 8.04 divided by 745. So I'm going to have 7.856 liters of hydrogen. At what pressure? At 745 torr. All right, these two have to add up to 100%, and so I'm just going to do this minus the from the 8.04, which is going to give me 0.183 liters of water vapor. Uh, 745 torr of water vapor. Okay, so we'll do the same thing. We're going to calculate how many moles of hydrogen, dry hydrogen, there are. Although I should have done it now, but just combined it. So the moles of dry hydrogen is equal to the pressure of dry hydrogen times the volume of dry hydrogen divided by RT, temperature of the dry hydrogen. The pressure of the dry hydrogen is 745 torr. The volume of dry hydrogen is 7.856 liters divided by R, 0.08206 liters times atmosphere per mole Kelvin divided by T, 293 Kelvin. So what does that give us? 745 times 7.856 divided by 0.08206 divided by 293. Oops, I forgot to convert to atmospheres. 1 atmosphere is equivalent to 764 divided by 760. I get 0.3202 moles of hydrogen. So we have the same answer, whether we did it Dalton's or Avogadro's. You see that? All right, let's take a break now and then we'll start it up again. What qualitative analysis is just trying to figure out what's present. There's something else called quantitative analysis. Quantitative analysis tries to figure out what's present and how much of it you have. So we just want to know, is it there or is it not there? So this would be similar to like let's say a COVID test. COVID test, you aren't counting how many viral particles you have. You just want to know, is it there or not there? And so this is kind of the same thing with qualitative analysis. The problem is it depends on the sensitivity of the test. So some of the COVID tests, they require certain viral loads to get a positive result. And so if you're below that, the test isn't sensitive enough to detect. Well, the same thing happens here. If you test negative, what does that mean? If you test negative, let's say you test negative for COVID, what does that mean? You don't have COVID, right? Or does it really mean that? You know, could it be possible that you do have COVID, but you're just at the early stages where the viral load isn't very high, or the late stages where the viral load is low? Well, the same thing here. It depends on the sensitivity of the test. Some tests aren't very sensitive. So if you do test negative, it's possible you could have had it present. It was just so dilute, in such low concentration, it was hard to detect. But for these tests, a positive test result usually means it's there. Usually, unless you have a problem with contamination. You know? It's the same thing if you go for COVID tests, there could be contamination. And so, barring contamination, a positive test means something. It means we have the species present. What are the species we're looking for? We're looking for ammonium, silver ions, lead 2 ions, barium, and manganese 2. Those are the cations we're going to look for, 5 of them. And then we're looking for 3 anions, chloride, sulfate, and nitrate. And what we have are simple chemical tests to detect the presence of these. Some are easier to detect than others. You know, it just depends on the sensitivity. Some are too sensitive, meaning that they're susceptible to interfering species. All right, so you want to read through this in preparation. And then we come to our first test. Our first test is detection of ammonium. Is ammonium ion present in our sample? This one, if the ammonium is too dilute, it's hard to detect. And so a lot of people get false negatives for this. That is, they test negative, but in reality, they actually had it there. And so something like this, the more volume you have, the more concentrated it is, the easier it is to detect. But how are we going to run this lab? And so the way we're going to run this lab is it's divided into 2 basic schemes. And the easiest way to see this is through these flow charts. And so the ammonium test is what we call individual test. We're just testing for ammonium. So we take a 3 milliliter sample. A 3 milliliter sample is about 3 squirts of the plastic pipette, or maybe about 3 thumbnail heights in the test tube. It doesn't have to be exact. If you get less than this, not a problem. If you get more than this, usually it's easier to detect with greater quantities. But the problem is you might run out of unknown. And so you're going to be given a total of 15 milliliters, roughly, of unknown, maybe more. They don't measure it out so precisely, probably 15 to 20 milliliters. Out of those 15 to 20 milliliters, you're only going to use 3 milliliters for this test. You know what people do? They use all 15 to 20 milliliters for this ammonium test. They're probably going to get pretty good results. They'll probably see it pretty easily. But the stockroom is going to be very unhappy when you go there to ask for another sample of unknown or known. In this case, we're going to be doing 2 things. The 2 things, actually more, the 2 basic things that we're going to be running are the known solution which is part 1. The known solution contains everything. So you should test positive for all the species, all 8 of them. The unknown solution is going to just contain select species. And we'll have some limited number of them. I'm not sure exactly how many we're going to put in. And so everybody's going to run the unknown and the known. You're first going to do the known so you know what things are supposed to look like. You're going to know about how much reagents you need. And you'll know what observations to expect. And so we'll run. So for this test, this is what we call an individual test. We'll get 3 milliliters. The way I'll set it up is like this. It looks like I take 3 milliliters of cation mixture. So the cation mixture I'm going to just divide into different portions. 3 milliliters of the ammonium, silver, lead, barium, manganese mixture. This is called the anion mixture. The anion mixture is actually a separate solution. The anion mixture, you don't have to go to the stock room. So if you need more anion mixture, you just take it off the bench top. It's not a problem. It's the cation mixture that you have to go to the stock room for. Okay, here it's not so clear what we do. We add some sodium hydroxide. Is that solid sodium hydroxide? Aqueous sodium hydroxide? If so, what is the concentration and how much do we add to this? I know 3 milliliters, I need that much, but how much of this do I need? And so I'll have to go back up to the procedure and take a look. And here we are. Identification of ammonium ion. This is the only cation tested with a separate sample of solution. So this is what I call individual test. Attach a moistened piece of red litmus paper to the convex side of the watch glass. Pour 3 milliliters of the cation mixture into a 100 milliliter beaker. Add 3 milliliters of 6 molar sodium hydroxide and quickly cover with the watch glass. Swirl gently, taking care not to splash the litmus paper. So they give us the reaction here. Ammonium plus hydroxide yields ammonium water. Ammonia is aqueous, but if you swirl this, some of it will come off as a gas, ammonia gas. Some of the aqueous ammonia formed will escape from the solution as a gas to contact the moist red litmus paper. So here's ammonia and water, goes to ammonia and water, which goes to ammonium and hydroxide. Well, this doesn't quite make sense. Ammonia, yeah. A uniform deep blue piece of litmus paper and the odor of ammonia gas confirms the presence of ammonium in the original solution. If these observations are not noted after several seconds, gently warm the solution. It should not get hot, with the watch glass still covering the beaker, and observe again. Observations of the solution upon addition of sodium hydroxide can give much information about the presence of other cations as indicated by the following equations. And so we'll take a look at those in a minute. And so this is what I do for the procedure. And this is what I do to prep to move fast in lab. The faster we can get through the known solution, the more time we can spend on the unknown solution. The unknown solution is going to be a little bit more complicated because it's missing some species. And when it's missing species, we aren't going to get all the same observations as we got for the known. And so the first test is ammonium present in our solution? So we have this known or unknown solution. We want to detect if ammonium is present. And here, what we're going to do is we're going to add sodium hydroxide. So rather than leaving it like this, I'd probably draw something like this. And so we have a 100 milliliter beaker. And then I'm going to dump in 3 milliliters of unknown aqueous solution. All right, then how much sodium hydroxide did it say to add? Three milliliters of 6 molar. And so over here, I'll just say 3 plus 3 milliliters of 6 molar NaOH. All right, then we're going to cover it with a watch glass. On the watch glass, we're going to wet a piece of red litmus paper and stick it on the underside here, on the convex side. So this is wet red litmus paper here. And it should adhere to the bottom of the watch glass. So we know ammonium likes hydroxide. When ammonium and hydroxide react, it's going to form ammonia and water. In other words, ammonium hydroxide decomposes into ammonia and water. Ammonia is aqueous, but we want a little bit of it to go in the gas phase, so swirling it might help. But ammonia is very soluble in water. And so we end up with NH3 gas here. Ammonia is a weak base. And bases will turn red litmus blue. And so the reaction for that is we're going to have ammonia gas hit the red litmus paper, which we call HILT. It's an acid. And so this is red. And when the base reacts with the acid, it takes the hydrogen, the proton. It's going to make ammonium, and we're going to be left with LIT minus. I don't write out the full formula for the anion. It's pretty complicated. But LIT minus is actually blue. So this is like phenolphthalein. Phenolphthalein in acid is colorless. And in base, when you add the base to it, it turns pink. Well, red litmus is red in acid. And when it goes base, it turns blue. So air is neither acidic nor basic. If we look at nitrogen, nitrogen's not an acid. Oxygen's not an acid. Neither are those bases, but ammonia is a base. And so the ammonia is going to rise up and gradually turn the color of the red litmus to blue. So if the litmus goes from red to blue, then that's what we call a positive test for ammonium in our original sample. You know, red to blue is a positive test for ammonia, but the ammonia came from the ammonium. And so we have a positive for ammonium in our original unknown solution here. So this is the flow chart. Something like this. Okay, we have to watch out, because if there's hydroxide here, any base will turn red litmus blue. So hydroxide is an even more powerful base than ammonia. Ammonia is a weak base, hydroxide is a strong base. So we want to watch out for splattering, because if splattering comes up and hits our red litmus, it's going to turn it blue, or splashes. But it'll look different because the gas will fade, gradually fade to blue, Liquids will leave splotches of blue on the litmus. And so we can tell the difference between splattering and a gas changing it. So the more gas we have in here, the easier it is to see that blue color. This test doesn't take too long, 5 minutes, less than 5 minutes. And so the individual tests, I usually recommend save those for later. Let's say you're boiling water. Boiling water takes a long time. So while you're waiting for the water to boil, you might as well do some of these individual tests. Okay. Now there are side reactions or interfering reactions that occur because our unknown is not just ammonium. Our unknown or known mixture is going to have ammonium, silver, etc. And so we're going to have some what we call interfering reactions occurring. So if this solution contains silver ions like hydroxide too. So if we add sodium hydroxide, silver and hydroxide combine to form silver hydroxide. Silver hydroxide is a precipitate. But 2 silver hydroxide formula units here can decompose into 1 silver oxide and water. And so that's what happens in this case. The silver hydroxide is replaced by the more stable silver oxide. Silver oxide is black, PPT. So if we see a black PPT form, we add the hydroxide to this, then that tells us, hey, we have silver in there too. And so silver can interfere in this test. What else can interfere in this test? Lead ions. Lead ions also like hydroxide. So lead plus 2 hydroxides yields lead 2 hydroxide. This is a white PPT. So if we see a white PPT, then there's lead present here. It's hard to see a white PPT when we have a black PPT together. And so these precipitates will, the black PPT will mask the white PPT. If there's manganese present, manganese loves hydroxide too. Manganese 2+ plus 2 hydroxides yields MnOH2 solid. This is a brown PPT. So for your known, you're going to get all 3 precipitates. So you're going to get a black, a white, and a brown precipitate. So the whole thing is going to look brown. And it's hard to distinguish, but your unknown might not have all 3. So in your unknown, you might just get the white precipitate. If you just get white precipitate, then you only have lead. If you get a brown precipitate, it's hard to tell. But you definitely have manganese and or silver. Okay, the anion test I'm going to talk about later. We're not going to be able to finish the whole thing tomorrow. So what I recommend is starting on this. This is a much more complicated analysis scheme here. And so we're going to need 12 milliliters of cation mixture. So make sure you save 12 milliliters for this or just dump out 12 milliliters. Again, they're going to give you more than 12 milliliters so you can run individual tests. So to the 12 milliliters of cation mixture, which contains ammonium, silver, lead, barium, and manganese, it's going to contain all these ions. We're going to go through this flow chart here. So it's the same thing. Rather than reading the procedure, I like to draw just little pictures of the steps. And so the procedure says get a large test tube. And then in this large test tube, put in 12 milliliters of unknown solution. Now this is not the real unknown. This is our known. So we know we have all the ions present. into a large test tube. To this, we're going to add some HCl. So how much HCl, what concentration? So here, I'm going to go back up and read the procedure. This is step B. Separation and identification of silver ion. Place 12 milliliters of calc-ion mixture in a large clean test tube. Add 3 milliliters of 6 molar HCl. And so they're telling us to add 3 milliliters of 6M HCl. All right. What we're going to get is we're going to get a precipitate here. We're going to end up with 2 white precipitates. The first precipitate is silver chloride. And so the silver ions that are present in the unknown react with the chloride ions present in HCl. The acid doesn't do anything here. It's what we call a metathesis reaction. And then ionic is just a precipitation like that. Silver ions, like chloride ions, to precipitate like silver chloride. This is going to be a white PPT. We're going to get that. And then we're going to have lead ions. Lead ions also like chloride ions. We need 2 chlorides for every lead. We're going to form PbCl2. This would be the net ionic equation for precipitation of lead. And it turns out that both of these are white precipitates. So we can't tell the difference. If we get a white precipitate, it could be silver chloride, it could be lead chloride, lead 2 chloride, or it could be both, a mixture of silver chloride and lead 2 chloride. This step is called the precipitation step, and it's what we're doing to separate the silver and the lead from everything else. Well, it's a little bit more complicated than what's shown here. So the HCl, the chlorides used to precipitate silver, as silver chloride here, you see the white precipitate. But what happened to my lead 2 chloride? Do you see it? This lead 2 chloride should precipitate also, but do you see it? I don't see it. What happened to it? What happened to it is the second step here. The first step is HCl. The second step is the heat. And that's what happened to it. And so this, let me write this in 3 milliliters. How much HCl do I need? Somebody asked you, how much HCl do you need? You need 3 milliliters, right? That's what the procedure says, add 3 milliliters. But, you know, you might need a lot less. You might need 0 milliliters. What if you didn't have any silver or lead? If there were no silver and no lead, what's the purpose of adding the HCl? You're adding the HCl to precipitate out the silver and the lead. But if your unknown has 0 silver and 0 lead, should you add all 3 milliliters? No. The answer is no. The answer is no, because if you add too much HCl, that causes trouble later on, is the HCl could potentially interfere with subsequent steps, and it does interfere with subsequent steps. So if you have too much unreacted HCl, that's a problem. Sometimes it's not enough. What if you had tons and tons of silver and lead? Is 3 milliliters enough to capture all of it? Maybe not, because what we need to do is we need to make sure all the silver is over here, because if silver ends up over here in this separation, that is, it's incompletely separated, then that silver can go on and cause interferences later on. Those interferences screw up all your precipitates, they screw up your colors. You get very confused because you don't know, you're expecting this, but you're getting that. A lot of people are saying, I was expecting a black precipitate, but I'm getting a white precipitate. I don't know what's going on. It's probably because incomplete separation and interfering ions. So how much do you need? And so when we're doing a separation like this, we need to do a complete separation. So we need enough for complete separation. And so what that means is if I'm getting no precipitate here, there's no point in adding more. And you stop. Or if you're getting a precipitate here, then what you do is you want to get all the precipitate out. In order to get all the precipitate out, this is just some general number. This is probably overshooting, or it might actually be undershooting. In fact, it isn't even 3 milliliters. You know what they say, how much to add? Let's see how much they say to add. Oh, 3 milliliters. It is 3 milliliters. But what we're going to do is we're going to ignore that 3 milliliters. What we do here is we just keep adding it. We keep adding it until we stop seeing it precipitate. And so you add until it no longer precipitates. But the problem is it's so hard to see. It's so hard to see, and it takes a long time for it to settle down. So this precipitate consists of very tiny crystals, and it's going to form a very cloudy white solution mixture. And so what you do is you wait for it to settle down. You want the precipitate to settle to the bottom of the test tube. Well, in order for it to settle to the bottom of the test tube, it might take a night. You might have to let it sit overnight. But if you did let it sit overnight, the precipitate settles down here, and then what we're left with is a clear, colorless solution over here. And then we add one more drop of HCl. If that one more drop of HCl causes more precipitation, then we didn't add enough. And so we keep adding until it stops turning cloudy. Eventually it's going to get too cloudy. We're going to have to wait, let it settle down, and then test it again. We test it again with one drop and see if it turns cloudy. If this one drop, it doesn't turn cloudy, there's no precipitate, then you're done. You've precipitated as much as you can out of that. And so what you do is you keep a rough running total. 20 drops is a milliliter. One squirt of the pipette's about a milliliter. And so we keep a rough running total. We don't have enough time to wait for this to settle down. And so we're going to heat it. There are 2 reasons why we heat it. Heat the mixture in a hot water bath. And so what we're going to do is we're going to go in the lab, and there's something called a hot plate. This is just a porcelain plate with a heater underneath. And then we're going to put a water bath here. So get a beaker, fill it with some water here. And then we're going to put our test tube there. Okay, as this gets hot, what happens are these tiny crystals collide with each other, and sometimes they get stuck together. And what we want them to get stuck together. This is called coagulation. So we coagulate these tiny crystals into bigger particles. Those bigger particles can sink. And so by heating this up, we speed up the coagulation process so that this can settle. And so we want the precipitate to settle near the bottom of the test tube, leaving us with a clear layer above it. And then we test the clear layer with additional HCl until no more precipitate forms. Is that clear? And so the amount of HCl you use is going to be adjusted depending on how the precipitation goes. And so there are two purposes for the heat. Number one, coagulation. That's step 2 here. So we add the HCl, we heat it and recheck it. Let's see, once no more precipitate forms, then the second purpose of the heat. The second purpose of the heat is this. Silver chloride and lead-2 chloride have drastically different solubilities in hot water. You can take hot water and try to dissolve silver chloride, you'll barely get any of it to dissolve. Whereas if you take lead-2 chloride in hot water, it dissolves. And we form lead-2 chloride aqueous. Lead-2 chloride aqueous consists of lead ions and chloride ions here. And they'll break apart the lattice. So the second purpose of heating is we want to dissolve all the lead-2 chloride. And so we're going to get a stir rod and try to crush up the crystals here to get them to dissolve. Not all of them will dissolve because if you have silver chloride, the silver chloride will remain. Just the lead-2 chloride will dissolve. And so that's what we're showing here. After you heat this and then grind up all the precipitate, all the lead will redissolve. The lead-2 chloride redissolves to form lead-2 ions and chloride ions, which is here but not shown. And the silver chloride will remain as a solid precipitate. So we have a pretty good idea. If you have a white precipitate here, it's most likely silver chloride. Now, how are we going to separate that precipitate? What we're going to do is we're going to filter it while it's hot and wash. And so what we need to do is we need to prepare some hot wash water. And so get another test tube in here and put water in it. This will be the wash water. The wash water will be DI. And so what we'll set up is a filter. There'll be some filter paper in here. And we're going to take our mixture and dump it in here while it's hot. If we let the mixture cool down, then the lead will precipitate out of the solution. And so the liquid phase will go through, and then the solid phase is going to collect on the inside wall of the filter paper. So you'll see some precipitate collect here. The liquid phase we call the filtrate. If the filtrate cools down, then it's going to cause precipitation of the lead again. So if the filtrate cools down, we'll heat it up later. But before we heat it up, we're going to make sure we filter all of this. There's some steps missing in here that I've really inserted. The next step is to wash the precipitate. The filtrate should contain lead, barium, and manganese too. And the filtrate is going to contaminate my crystals here. So I want to make sure I wash it. Also, I have a finite amount of lead, barium, and manganese. And if I lose some of the lead, barium, and manganese, it's going to be harder to detect later on down the road. So what I need to do is I need to wash off the precipitate. I'm going to wash it in 3 washes. I'm just going to use a little bit of water. And so the first wash I'm going to keep. And so I'll use a little bit of this hot water to rinse off the crystals. And what I want to do is I want to rinse off most of the filtrate that's caught on the crystals. And so any barium, manganese 2, and lead ions stuck on here will be washed into the beaker. This will be filtrate. So the first wash, keep. We don't want to use too much water. We don't want to use too little. You know, if we use too little, then the crystals will be dirty and we won't capture all the ions in the filtrate. We'll leave some ions here which could interfere with subsequent tests. The second and third wash we discard. So what I'll do is I'll replace this beaker, the filtrate beaker, with a waste beaker. And then what I'm going to do is I'm going to thoroughly wash my precipitate. So it's as pure as possible, pure silver chloride as possible. So discard in the waste. Leave the waste there. And then what we're going to do is we're going to test our precipitate with sodium hydroxide. What should the sodium hydroxide do to the silver chloride? What we should see is we should go from a white precipitate to a black precipitate. And so the sodium hydroxide, we just add it to the precipitate stuck in the filter here, and see if we can convert it in from white to black. What's happening there is that the silver chloride solid plus the sodium hydroxide is going to give us silver hydroxide plus sodium chloride. 2 of the silver hydroxides can decompose into silver oxide plus water. This is the black precipitate. And so all we're going to do is we're going to convert our solid from white silver chloride to black silver oxide by adding sodium hydroxide, which is going to cause this reaction to occur. Okay, once we get that black PPT, we're done. A black PPT means we just tested positive for silver ions in our original unknown sample. This Ki is actually Ki solution. This is NaOH solution, 6 molar. I think this is 3 molar or 6 molar Ki. So what we're going to do is we're going to take our filtrate, which we separated off earlier, and the filtrate is going to contain lead, barium, and manganese. What can happen is the filtrate can cool down. As the filtrate cools down, the PbCl2 reprecipitates. We don't want the PbCl2 to reprecipitate. So if you start seeing white precipitate form in here, heat it up. By heating it up, you should see the precipitate disappear. If the precipitate doesn't disappear, then start stirring it to get it to disappear. We want it all to dissolve completely. Once you get it all to dissolve and we have a nice clear solution, we're going to add potassium iodide. And potassium iodide is going to be used in our next separation. We're going to precipitate out lead-2 iodide. So how much potassium iodide do I need to add? How much potassium iodide do I need to add to this? It doesn't matter the amount. It could be a little bit or it could be a lot. So for example, if we didn't have any lead there, and then you start adding the potassium iodide, what we're expecting to see is a yellow precipitate. If there's no yellow precipitate forming, what should you do? Should you keep adding and adding and adding? No, you should stop. Or you get lots of yellow precipitate. If you get lots of yellow precipitate, then when should you stop? Yeah, until you don't get any more precipitate. How long does it? I don't know. How much is it? I don't know. You just keep adding until you don't see any more precipitate, because if you don't get all the lead out, then the lead's going to screw up these results. You're going to get weird results over here. So we got to make sure we get all the lead out in this step. And so what that means is we might have to wait for it to settle, or we might try to coagulate it on a hot plate, so that the precipitate can settle the bottom of the test tube. That way we can test the solution above to see if we get more yellow precipitate forming. Okay, so now I've added enough Ki to completely precipitate out all the lead. I'm not getting any more yellow precipitate forming. Then what do I do? What I'm going to do is I'm going to do the first wash. The first wash, do I keep the first wash or do I discard the first wash? I keep the first wash. So I'm just going to wash this a little bit. Why? Why am I going to wash this? I'm going to wash my precipitate because it's contaminated with barium and manganese ions. But I don't want to lose those barium and manganese ions, because if I lose those, it's going to be harder to detect. And so I'm going to try to make sure I don't lose it by washing off the barium and manganese ions in the solution, in the residue here, into my filtrate. And so my first wash is going to be keep. So I'm going to clean the funnel, get a fresh piece of filter paper, and then filter it. Okay, and then I'm going to wash. Normally some lead-2 iodide is stuck in the beaker or stuck in the test tube, so you need to rinse that in there anyway. Okay, then I wash it, keep it. Do I need to do a second and third wash here? Over here, I don't need to do a second and third wash, because I don't care if this is clean, all that clean. Here, I wanted this to be clean. I needed this to be clean because I have one more step here. And if there are interfering species here, it's going to screw up this test. Over here, am I doing any subsequent tests on this? No. So if I have a yellow precipitate and it's visible, then it doesn't have to be super clean. And so I'm going to forego the second and third wash. So I'm just going to do a first wash so I don't lose any barium and manganese. That's it. Okay, so yellow precipitate here means we had lead, 2 ions in our original unknown. Then what I'm going to do is I'm going to take the filtrate and then add some sodium bisulfate solution to this. With the sodium bisulfate, I should get barium sulfate to precipitate. I'm going to keep adding until I stop seeing barium sulfate form. However much that takes. Okay, once it stops precipitating, then I'm going to wash my precipitate. The first wash, am I going to keep or discard? first wash I'm going to keep and combine with the filtrate. If I were to do the second and third wash, I would discard, because that's just going to overly dilute. The more dilute this is, the harder it is to detect. And so this is why we're just going to keep the first wash here. We're not even going to bother doing a second and third wash because there are no subsequent tests. So if we get a white precipitate here, we're done. It tests positive for barium ions. Now for manganese ions, here, we're going to add sodium hydroxide. We're going to get manganese 2 hydroxide, light brown precipitate here. Here, do I keep the first wash? So if I wash this and I combine it with the discard solution, since the filtrate in this case is going to be thrown away, I'm going to discard the washes. How many washes should I do? Should I just do one and then forego the second and third wash for this? Or should I do all 3 washes for this? All 3. We need to do all 3 washes. We need this to be clean. Otherwise, it's going to screw up this result here. And so I'm going to wash this 3 times and discard all the washings. Hopefully I have precipitate left. And then to the remaining precipitate, I'm going to dissolve it in nitric acid. How much nitric acid do I need? I need enough to dissolve all my precipitate. And then I'm going to add this. This is called sodium bismutate. This is a solid. Nitric acid is a solution. So I'm going to take a small scoop of this. This is a powerful oxidizer. So try not, it's a very, very fine brown dusty powder. Don't create a dust cloud there, because if you inhale this stuff, it'll cause a lot of damage to your throat, lungs, and whatnot. And so sodium bismutate, what that does is it oxidizes. So we dissolve this, all the precipitate in this acid, and then we're going to convert the manganese 2 ions into permanganate, MnO4 minus. Manganese 2 ions in solution have a light pink color. So, do you know what the color permanganate is? It's like grape juice. It's a deep purple color. And so what we need to do is we need to add the solid sodium bismutate to this solution. There's 2 steps here. To this solution after dissolving the precipitate. And that's going to convert that solution into a purple grape juice-like solution here. And once we get that, it's positive. It's not a solid. A lot of people are looking for precipitate. The dashed lines mean solution. The solid lines means precipitate here. Although this is a solution here. I don't know why they didn't dash it. All right, so this is the longest sequence here. The other sequences are short, so start with the longest.
What kind of flux would you recommend for this lab?
Well, lead is a heavy metal. And so you definitely don't want lead on your hands.
Is there a latex solution?
I don't even recommend latex gloves. Let me see what gloves I recommend. There. I'll show you the gloves. How did they close? A lot of glove manufacturers supply a chart like this. You know what I mean? I think they, can't imagine they want you to buy this. Red is not recommended. Green is good. Yellow is borderline. So latex is this third column here in the gloves. You can see lots of red. It depends on what you're using. Let's take a look at some things. What are we using? We're using aqueous solutions. So there's some things that are good for nitrile that aren't good for latex. And there are certain things that are good for latex which might not be so good for nitrile. So if you're using butyl alcohol, latex is preferred over nitrile. But when we look at most of these, this is not rated. When we look at most of these, nitrile is superior. There are a lot of pores here where nitrile is excellent. Excellent, E, G is good. And so I recommend nitrile gloves. Nitrile gloves also breathe more than latex gloves, so they're more comfortable. Okay. You want to be aware of chemical risks. We're going to talk about this tomorrow as well. Whenever we're thinking about working with hazardous chemicals, we want to consult the SDS or the MSDS. The SDS are the safety data sheets. And so we want the SDS for lead 2. We want something soluble. It can be lead 2 iodide. We're working with lead 2 iodide. That's the yellow precipitate. So this is the acute toxicity, carcinogenicity, reproductive toxicity, etc. So we read the warning. After reading this, you may not want to work with this at all. May cause cancer. May damage fertility or the unborn child. May cause damage to organs through prolonged or repeated exposure. Very toxic to aquatic life with long-lasting effects. Do not breathe dust, fume, gas, mist, vapor, spray. Wash skin thoroughly after handling. In case of skin contact. So, OSHA is usually written for people who work with this day in, day out. And, there are a lot of lead pigments in paints. The beautiful orange precipitate gives a beautiful orange paint, And so a lot of these things, when you read, like gasoline's the same thing. Gasoline's a potential carcinogen. If you start reading these, then you get a better idea of it. And so what we want to do is we just want to be able to handle this safely without poisoning ourselves, without causing harm. And so we'll take special precautions to do that. And so you shouldn't have to touch any lead. But anyway, we could read the SDS for all the chemicals. If we look at silver, what we're going to be using is silver nitrate. It seems a little better. Maybe corrosive to metals, may cause burns, etc. And so lead we want to be especially careful with. Also the sodium bismutate we do want to be very careful with that. And so just avoid contact with lead. You know, as with other chemicals. All right, are there any questions on this? All right, so read through the lab for tomorrow. We're not going to make it through the whole thing tomorrow.